Hello everyone, welcome to Solid State Physics course. Okay, Do- Doris. Okay. అది ఇప్పుడే తిప్పేస్తే మీరు వెళ్ళిపోండి. Hello everyone, welcome to Solid State Physics course. Okay, hello everyone, welcome to Solid State Physics course. So in this course, Unit 1 is completed. Now we are coming to Unit 2. So in the part of Unit 2, Lecture 1 is about crystal planes. In this lecture, we are going to cover about crystal planes. Okay, let us discuss about crystal planes. Okay. Hello everyone, welcome to Solid State Physics course. The last lecture. Hello everyone, welcome to Solid State Physics course. So previously we have completed Unit 1. Now we entered into Unit 2. This is lecture 1 is about crystal planes. Okay, in this lecture we are going to discuss about what is crystal planes. Hello everyone, welcome to Engineering Physics course. Previously we have completed Unit 1. Now we are going to discuss about Unit 2. So the part of Unit 2, first lecture is crystal planes. Today we are going to discuss about crystal planes. So let us discuss about crystal planes as a part of Unit 2. Before that, we just try to see what are the topics we are going to discuss in Unit 2. First, crystal planes. Next, importance of crystal planes. That means how to index these crystal planes, that is Miller indices, what is the important features of the Miller indices that we are going to discuss. And also interplanar spacing and Bragg's law and its limiting condition. Finally, we are going to discuss about X-ray diffraction. There are experimental techniques of X-ray diffraction. Okay, so before going to this one, just in Unit 1, we have discussed about crystal, lattice, basis, crystal structure, what are different types of lattices are there, and crystal system, how many crystal systems are present, how many Bravais lattices are present, atomic packing factor, those things we discussed in Unit 1. There I have given some assignments. In addition to that, I have given some optional assignment. So first thing is density of crystal there. So I just given what is the density of the, how did you do that? Just I am trying to again I am trying to recollecting the density of crystal. Just I want to mention about the formula of density of a crystal is mass of the unit cell by volume of the unit cell. Of course many of you have done this one. Okay, those who are not done, just follow this one. Density of a crystal always mass by volume, that is unit cell, because it is a unit cell is a basic unit for the crystal, so that if you know about the density of unit cell, then you can know about the density of the crystal. So mass of unit cell, you know about molecular weight by Avogadro number, that's will give the mass. And so the density is given by Nm by Na into A cube. Volume of the unit cell is A cube. So you can easily calculate this density of the crystal. And next, second question. Second question in optional assignment, I given number of atoms per unit cell for hexagonal crystal. In case of hexagonal crystals, as you can see, the number of atoms per unit cell here, if you carefully observe here, there are three different atoms are there. One is corner atoms, another one is inside the unit cell, three atoms are present, and finally here face centered atoms are present. If you look at here, again how many face centered atoms are there? Two face centered atoms are there. So one face centered atom is shared by the two unit cell, so that it is 1 by 2 atom present in this unit cell. 1 by 2 plus 1 by 2 is 1. So from the face center it is 1 atom, and inside again 3 atoms, that is ideally within the unit cell is there 3. 3 plus 1 means totally 4. 4 present inside the hexagonal unit cell. And what about corner atoms? Corner atom, each corner atom is shared by the 6 unit cell. How? Let us see this corner atom. Here 1 unit cell will be present, 1. Here next 2, and again 3. And top also 3. Total 6 unit cells shared by the 1 corner atom. That means 1 by 6 is present. How many corner atoms are present? Here on top 6 and bottom 6. There were 12 corner atoms are present. 12 into 1 by 6 means 2. So 2 corner atoms, 3 inside the crystal, that means 5, 1 face centered atom, totally 6. So number of atoms per unit cell is 6. So many have done this one exercise. Okay, those who have not done, for them only just I am repeating. Okay, now we move on to the crystal planes. Today's topic, crystal plane. What do you mean by crystal planes? So crystal plane is basically, again I have given some assignments. Okay, I ask you to construct a models. See, some of them has done models. So atoms are packed like this and it forms a unit cell. Now if you take these atoms as a plane, one plane, that means if you consider it as a one plane, that plane is having the large number of atoms. That just imagine it is a plane. Not exactly plane is there. That is a plane is there. So that planes are called crystal planes. So like this, if you see body centered cubic, this is also one model. This is a plane. This is also one plane. In between also one plane. You imagine like this. So on top one plane, bottom one plane, like this. But as you know, there are continuously atoms are arranged continuously. So you consider as each and every two-dimensional part you take, it is a plane. That plane is having the many number of atoms. So those are basically called crystal planes. So how to define crystal planes? Crystal planes are imaginary planes are having large number of atoms. The atomic density is there. That is called crystal plane. How these planes are look like? In two-dimensional, these planes we represent with a parallel lines. So these are the lines. So this is one plane, another plane, one plane. So this is another type of plane which is having different orientation. This is also another plane which is having different orientation. This is also another plane of different orientation. This is two-dimensional representation. Now if you see in three-dimensional, the real crystal is like this. Okay. Now if you see green colored atom, this is one plane, and blue color, violet color, this is another plane, again one plane, and alternative planes are present. This is called atom planes. That imaginary planes, we just imagining the planes are here. Okay. So same thing if I draw in a unit cell form. This is one plane, this is one plane, this is one plane, this is one plane. For simple cubic, body centered again, one plane, this is different plane, this is one plane, different plane. Like this. See here, individually the planes for simple cubic, like this, body centered cubic different, face centered cubic is different. Similarly, if you take a unit cell, the planes, these are the parallel planes. All planes are parallel. Here if you say more number of planes, same planes which are having more number of, like this, if we extend in all directions, these parallel planes are always present in the crystal. See, this is a green color. These different orientation of the planes are there. Just I am showing here that there are different planes are exist inside a crystal with the different orientations. So those orientations you can see here. This is another orientation. The plane is triangular shape. So this is also parallel planes. And also this is more number of planes are present in the crystal. And this is another orientation of the planes in the unit cell that you can see. And these are as you can see, these are parallel planes which are exist inside the crystal. And now this is the plane in one unit cell. This plane is parallel to another plane. So both are also is having the planes inside the crystal. So this is also the same orientation of the planes, different planes are present. Now here different orientations or different planes are present inside the crystal. So from this what we can understand, in a crystal there are n number of planes are there. The planes or shapes are different, the orientations are different. So based on the different orientations, we can name it to the different planes. So that what is about crystal planes. So I hope you understand about crystal planes. So crystal planes basically there is imaginary planes which it doesn't exist really, but we can imagine the planes are present inside a crystal. That we can see inside a crystal, or we can imagine the crystal. If you know about the planes, then you can know many information about the crystal. That also we can find in a, it is basically helpful. These planes are, information about these planes are really helpful to understand about crystal structure and crystal system of the planes. So planes are oriented different directions. Now just I want to give some assignment. So what do you mean by crystal planes? Just I want you to write in your own words what is the crystal planes and construct a model having the different planes are here. Does the crystal plane has atoms? Is that really the planes are having atoms or not? That thing you have to mention in the assignment. Okay. Now with this, so in today we discussed about crystal planes exist inside a crystal, how the planes are exist, how planes are oriented, how many different orientation of the planes we have seen, with some illustrations we have seen. Okay. So again tomorrow we'll meet with another lecture that is about Miller indices. Okay, thank you. Hello everyone, welcome to Solid State Physics course. In Unit 2, today we are going to discuss about Bragg's law. Okay. Hello everyone, welcome to Engineering Physics course. Today we are going to discuss about Bragg's law in Unit 2. Okay. Let us discuss about Bragg's law. Before that, just try to recollect what we discussed in a previous lecture. In previous lecture, we have seen interplanar spacing for a cubic system, in general crystal systems, that we arrived some expression d is equal to a by square root of d is equal to 1 by square root of h by a whole square plus k by b whole square plus l by c whole square. And also for cubic system, d is equal to a by square root of h square plus k square plus l square. That what we discussed. There we have seen the parallel planes. Okay, this is the model constructed. Okay, so we have taken one normal. This is like a normal we have taken, and we taken one plane. So this is the plane. If you remember, this is 1 1 1 plane. Normal you have taken. So from this normal we have taken one normal from here. The distance between from this plane to this plane, that we have taken as a D, interplanar spacing, because we imagine this type of parallel planes are exist inside a crystal. This is here one plane, this is one plane, this is normal distance we have taken, that is interplanar spacing. That what we discussed in the previous lecture. Today the same thing, if you see the parallel planes are how it will look like, that also we have seen in the last class. And now if you take these planes, okay, if you take these planes, if you take these planes, so all the atoms are here, this is one plane, and again this is also one plane. That atom is one plane, this is also one plane. So this is also one plane, this is also one plane, this is also one plane. That means this total atom I am represented with a small dot. This is also here small dot, this is also small dot, this is also small dot, this is also small dot. That means parallel planes are present, parallel planes are present, okay. Each and every atom if I represent with a small dot, okay, like this. Now if we have something, that means some incident radiation is incidenting on it, that means some X-rays or some rays are incident on this plane, on this plane. This plane is having so many number of atoms, the atoms is having the electrons, and whatever I say it is X-ray, X-ray is a electromagnetic wave, it is a EM wave. Then electromagnetic wave will have a electric field. The oscillation of electric field is there. Again there is a electrons are there, negative charge. This electric field is interacting with the electrons in the atoms. Then there is a scattering will takes place. Whenever there is a scattering will takes place from this plane, the X-rays will get scattered. Okay, X-rays are getting scattered. So that we can easily understood, whenever there is a radiation incident on atomic plane, there is always scattering will takes place. Now I just wanted to draw same thing. If you take a atoms as a points are like this here, so this is one plane and another plane is also here, this is also another plane, these are all atomic planes, just I am representing like this. And if you take another parallel plane is here. Now what happened if the radiation incident on these atomic planes, from the planes the radiation will get scattered, this is scattering will take place like this. Just I am drawing ray diagram. So again some other radiation will incident on the bottom plane, again there is a scattering will takes place. So if I say the angle of glancing angle, if I take it as a theta, if the rays incident on with an angle theta, glancing angle theta, then it is scattering. Now I just wanted to find what is the path difference between these two rays. For example, these two rays are coming from here, or if you say it is ending here. Now the length of this one, this ray length is equivalent to, for example, if I draw a normal from here to here, it is a normal, then the length of this one and length of this one is equal. Geometrically it is equal. For example, if I say it is O, it is O dash. If I say it is P, it is P dash. So it is incident on a point A. Here if I say it is a point A and this is point B. So whatever the normal, if I say it is C, that means from this geometry we can understand O dash A is equivalent to the OC. This length is equivalent to this length. Similarly, if I draw a normal here, this is a normal. If I say it is D, then the distance AP, the length AP is equivalent to the length DP dash. This is equal, obviously. That means the ray 1 is traveled from O dash incident on A, it is reflected and reached at point P. And second light ray, if I imagine second ray from O, it is incident on B, it reached at a point P dash. So both are reached at this point P and P dash at the same time. That means the extra length, that means this ray has traveled more length as compared to this ray. That means ray 1, if I say it is ray 2, this is ray 1, ray 2. That means second radiation is traveled more distance as compared to first. How much more? Means this is same, both are same, this length also both are same. Whatever the additional length is there from here to here, this additional length is more length traveled by the second ray. What is that? That length, if I say it is a path difference, delta is equal to CB plus BD. This is the additional length traveled by the second light ray. If you know the additional length, that means path difference is there. What Bragg's law is saying, what Bragg is proposed that whenever there is a radiation, especially if you take X-rays, incident on a crystal, there is a diffraction taking place. There is a diffraction. When X-rays incident on a crystal planes, diffraction is taking place. That means whenever these two scattered rays are there, these two rays are producing diffraction pattern. Diffraction pattern, when it will produce, there should be constructive interference should take place. That means these two will have something constructive interference will take place, so that we will get some diffraction pattern, that bright dark like that. Okay. That means if it is the constructive interference, then what is the relation? For constructive interference, what is the condition? Delta path difference should be equivalent to the n lambda. That you know very well. In plus 2 also you have studied this one. If the path difference is equal to n lambda, it is constructive interference. If the path difference is equal to 2n plus 1 into lambda by 2, it is a destructive interference. So here diffraction is taking place. So we imagine it is a constructive interference. Then delta is equal to L lambda. Okay. So that means what is the path difference here? CB plus BD. So this we are going to find. So for example, if I draw a normal here, from here to here, what is the distance? This is one plane, this is another plane. The perpendicular distance between two planes is, we know it is a interplanar spacing. That is a interplanar spacing. That means that is D. So if this angle is theta, this angle also theta. These two are identical angles. Okay, this is theta, this is also theta. So from triangle, okay, from triangle ACB, from triangle ACB, I just want to find CB. So I have taken sin theta. Sin theta is equal to CB by, it is AB. That means CB is equal to, AB means what? Interplanar spacing. That means AB sin theta, that is equal to, this is D sin theta. Similarly, if you take another triangle, this triangle you take ADB. In this triangle, sin theta is equal to how much? This angle is also theta. Sin theta is equal to how much? It is, we need what is the value? BD. So BD by AB. Again it is BD is equal to AB means D sin theta. So this is 1 and this is 2. From 1 and 2, CB is equal to D sin theta, BD is equal to D sin theta. What is the path difference? Delta is equal to here CB plus BD. CB means D sin theta, BD means D sin theta. That means it is 2D sin theta. Now for constant interference, delta is equal to N lambda. If the path difference is equal to N lambda, then it is a diffraction is taking place. That means from these two, what you can write, 2D sin theta is equal to N lambda. So this is called Bragg's law or Bragg condition. So what Bragg's law is saying, whenever there is a diffraction is taking place from a plane, crystal planes, then always there is a condition should be satisfied. 2D sin theta is equal to N lambda. D means interplanar spacing, theta is glancing angle, lambda is wavelength of incident radiation, N is order of diffraction, whether you are looking at first order, second order, third order. That is the order of diffraction. This is called Bragg's law. But Bragg's law is also some limiting conditions are there. What is the maximum value will have? For example, always we see about first order diffraction. That means N is equal to 1. If N is equal to 1, then 2D sin theta is equal to lambda. That means lambda by 2D is equal to sin theta. What is the maximum value of sin theta? Always maximum is 1. That means sin theta is always less than or equal to 1. That means lambda by 2D it should be less than or equal to this 1. So this is the limiting condition of the Bragg's law. That means lambda should be less than or equal to 2D. That means then only diffraction will take place. If lambda is greater than 2D, then there is no diffraction will take place. So that is a condition for the Bragg's law. So now this is Bragg's law. ఇది నోట్స్లోకి వెళ్ళాను, మళ్ళీ వెనక్కి రావట్లేదు. ఒకసారి ఆపండి.